Okay, this video is on section 7.3, which is symmetric matrices and orthogonal diagonalization. Now, in order to understand this section, we need to first understand what regular diagonalization of matrices is. That's something that you may have seen in another class like Math 252, but it's also possible you have not seen it. And so, let me talk about it. You start with a matrix A. And let's use 3, 2, 1, 4. And this matrix is obviously not diagonal. And just in case you forgot about that, a diagonal matrix is when your matrix only has non-zero numbers on the diagonal and everything that's off the diagonal are all zeros. So that's an example of a diagonal matrix there. And my A here is definitely not diagonal. We have this 2 and this 1 there that shouldn't be there. But we're going to do something to it to kind of turn it into a diagonal matrix in some way. And the whole process is to find the eigenvalues and eigenvectors. And so let's go ahead and do that here. The eigenvalues, you solve the problem determinant of A minus lambda I equal to 0. So you would take A minus lambda I is 3, 2, 1, 4 minus lambda times the identity. And this works out to be the matrix 3 minus lambda, 2, 1, 4 minus lambda. And then we're going to take the determinant of that. And whatever we get, we're going to set it equal to 0. So this would be 3 minus lambda times 4 minus lambda minus 2, which is lambda squared minus 7 lambda, and should be plus 10. And we set that equal to 0 here. And we can factor that. And just to give you a heads up, any one of these I give you will be nice and factorable. You'll have nice solutions for your lambda, so you don't have to worry about quadratic formula or anything else crazy there. Now, once we have our lambda values, then we're going to look to try to solve the equation A minus lambda I 0 and solve the system of equations here. And so if I plug in lambda as 2, I would have the following. Sorry, this is actually after the reduced to echelon form. So initially I'd get this, and then after the RREF, I would have this here. And if you're trying to solve this, you write out the first equation. X plus 2y is 0. Y is my free variable, right? I only have one pivot here. And so that means x is negative 2y. So xy is negative 2y, y. So that means everything is a multiple of the vector negative 2, 1. And that right there, the negative 2, 1, that is the eigenvector. So the eigenvector here. And again, for specifically lambda is 2, is the vector negative 2, 1. Then if I repeat the same thing here with my other lambda, if I do lambda now is 5, then I would have negative 2, 2, 0, 1, negative 1, 0, RREF that. X minus y is 0, x equal to y. So then my solutions are y times 1, 1. And so that's my second eigenvector. And then the final thing that we're going to do here, this is why it's going to be called diagonalization, is it turns out that you can check this yourself, that the matrix A, which is 3, 2, 1, 4, is going to give you the same answer as if you did the matrix negative 2, 1, 1, 1 times the matrix 2, 0, 0, 5 times whatever the inverse of this matrix is here. So you notice here that this middle part, this is diagonal. And also we notice that this matrix here is the same as this one, just being with an inverse on it. So we usually write this as P, D, P inverse, where the D is the diagonal and the P is this matrix that contains the eigenvectors. And this is what we call diagonalizing a matrix. So the whole point of a diagonalizing matrix is you find the eigenvalues, eigenvectors, and you write them out in this PD, P inverse format, and that is what is the diagonalization of the matrix A. So again, A is still not diagonal, but the D part is, and this all together makes A. So you're kind of breaking A up into these different matrices, the middle of which is diagonal. And let me kind of show you exactly why we do this, or at least one of the reasons why. Let's suppose you wanted to take a matrix A and raise it to, I don't know, the 100th power. Well, that would mean you would write this matrix down 100 times, and you'd have to do the multiplication 100 times, and that would take absolutely forever. But if you instead rewrite the matrix A as PDP inverse, then I would write down PDP inverse 100 times, which doesn't really look any better at first. But in the middle, a lot of nice things are going to happen. These P inverses and P's cancel each other out. That's what inverses do. And you're going to be left with a P in the front, and then a bunch of D's in the middle to 100, and then one P inverse at the end. And again, you might say, well, that doesn't really seem any better. We still have 100th power of a matrix in there. But it turns out that if you have a diagonal matrix and you raise it to any power, including 100, you don't have to write it out 100 times and multiply it. All you have to do is take the power of the diagonal elements and leave the zeros alone, and that's going to be right. So in this case here, with this previous one, where I had A to 100 is 3, 2, 1, 4 to the 100, it's going to be P, D to the 100, P inverse. The P matrix was -2, 1, 1, 1. The D matrix was 2, 0, 0, 5 to the 100. And then the inverse here is -2, 1, 1, 1 inverse. And we can do 100 now. I mean, I picked a number that was maybe a little larger than it'd be nice. 2 to the 100 is pretty large, and 5 to 100 is even larger. But it's something that can be done on a calculator or a computer. And then once you've done that, you just have to put together a couple of steps. You know, just multiply 3 matrices together, and you'd get the answer. So one of the most useful applications of diagonalizing a matrix is in order to be able to take powers of matrices, which otherwise would be next to impossible to do. Now all of this is regular diagonalization of a matrix. And so now we're going to transition into what is a orthogonal diagonalization.